The life and death of stars. In this lesson, we're talking about protostars, fusion, low mass, intermediate, and high mass stars, the life cycle of our sun, neutron stars, black holes, and HR diagrams.
Stars. When you look at the sky at night, all the tiny points of light you see are stars. Each star is a massive, burning ball of gas like our sun. And like our sun, each one was created and will eventually die. In fact, due to the speed of light, most of the stars you see in the sky are already gone. So all these points of light, that guy, every single point of light that you see on this diagram here represents a star that could be very similar to our sun. Some will be bigger, some will be smaller. They won't necessarily be based on how bright it is in the sky on this picture, because if a star is really close, it will appear brighter. The biggest stars could be the ones that are the most dim, and they're just really far away. Even areas that don't look like they have any stars, if you were to zoom in with a very powerful telescope, you would notice that there are stars there as well. All stars begin their lives as a nebula, which are huge clouds of dust and gases, mainly hydrogen and helium. These dust clouds bump into each other and combine. As the clouds get bigger, their gravitational pull gets stronger, and they attract more particles. Once enough particles are together, a protostar forms. Protostars become stars, and fusion begins. So basically, if we have a hydrogen here, and a hydrogen here, and here, eventually they come close enough together, and they form an area where there's more hydrogens. And I'm drawing 3, but there's obviously many more molecules. This guy right here has a greater amount of gravitational pull than the individual hydrogens off to the side. When they're all together, and there's enough of them, they're able to start bringing in hydrogens and heliums from around them until the cloud of gas gets bigger and bigger and bigger, and eventually coalesces into a protostar, which can begin fusion and become a star. Star life cycle. Fusion, combining 2 hydrogen atoms to form a helium atom and a huge amount of energy. Basically, it's hydrogen plus hydrogen gives you helium and a lot of energy. Eventually, that fuel runs out, and the star becomes either a brown, red, or white dwarf, a neutron star, or a black hole. What the star becomes depends on its initial mass. So how many of those hydrogens were there initially, that's the initial mass. Now, this star life cycle diagram we're going to come back to over and over again in this lesson. Low mass stars. Low mass stars are going to have a mass less than our sun, about 8 to 40% of our sun's mass. And they're going to be brown and red dwarfs. They're going to use their fuel very slowly, and they're going to last for a very long time. A low mass star can be around for about 100 billion years. Low mass stars simply die by burning up their fuel to leave behind a white dwarf about the size of the Earth, which themselves cool and turn to black dwarfs. Now, black dwarfs are really, really hard to see because it's a black object in a black region of space. Intermediate mass stars. Intermediate mass stars are like our sun, so they're about 40 to 800% of the mass of our sun. So about half, if you will, a little bit less than half, to about 8 times as large as our sun. They last for about 10 billion years. So you can see as we get to an intermediate sized star, we're going to use our fuel faster. When the hydrogen is used up, the core collapses, which causes the outer layer to expand, and that's going to turn this star into a red giant. It's going to get much, much bigger. So you can see the process. We have our nebula here, like we talked about the cloud of gas. That's going to turn into our intermediate mass star. That's like our sun. When our sun runs out of fuel, it's going to become a red giant. It's going to expand a huge amount and become a red giant. It's then going to become a planetary nebula and turn into a white dwarf. Now our sun's going to become a red giant in about 5 billion years. So we've already used about half the lifespan. So we've used about 5 billion years. We have about another 5 billion years, and then it's going to be a red giant. When it becomes a red giant, its outer diameter will expand past Earth. So if you think about how big the sun is right now, let's just call the sun right there. After the sun, you're going to have Mercury, you're going to have Venus, and you're going to have Earth. And obviously this is not to scale. But when the sun becomes a red giant, its reach is going to expand all the way out past Earth. So it's just going to be a massive, massive object in our solar system. And then eventually it's going to become a white dwarf, which is made up of carbon and oxygen. Life cycle of our sun. So there we go, we got our birth. And then, as I said, we're about 5 billion years, so 4.5 billion years. And then eventually, in about another 5 billion years, we're going to get our red giant, and then our planetary nebula, and then our white dwarf at the end. So right now, during its main time of life, so pretty much here to here, that's when it's going to be in the main sequence. That's when we're going to fuse our hydrogens to make heliums. In about 4.5 to 5 billion years, it's going to leave the main sequence and become a red giant. And in about 10 billion years, it's going to die out. Now that's an intermediate mass star. A high mass star, that's going to be about 8 to 25 times the mass of our sun. It's going to consume its fuel very fast. It's going to die more quickly and much more violently. When it dies, it's going to explode, creating a supernova, followed by a neutron star. So you can see we're going to take this bottom path now. We have our nebula. We're going to go to our high mass star, and then our red supergiant, which is just like a red giant, but just bigger. It's going to go supernova, and then it's going to become a neutron star. Now, neutron stars are incredibly cool. As their name would imply, they're made of neutrons, because their protons and electrons were smashed together when the star collapsed. If you take a basic idea of what an atom looks like, you're going to have your protons and your neutrons inside the nucleus, and then you have your electrons on the outside. What happens when a high mass star dies is everything gets smashed together, and the only thing that's left in the end are just these neutrons where the nucleus used to be. So now you can get a whole bunch of different particles, a whole bunch of different atoms squished into the same area. And that's going to give a very high density. They are so dense, everything is squished so close together that you can get an object 2 times the mass of our sun in a sphere approximately 19 kilometers in diameter. A sugar cube's worth of neutron star, so just one of these, just that guy right there, would weigh approximately 400 billion kilograms. Thor's hammer and neutron stars. So according to theory, Thor's hammer was created in the core of a neutron star, but if it was created from a neutron star, it would weigh approximately this much. Dropping on the ground would be like the dinosaur killer asteroid smashing into Earth. So what I'd like you to do is pause the video and watch number 4. It's a really interesting look of what it would be like if Thor's hammer was actually made from neutron star material. Black holes. Now, black holes can be formed from stars whose masses are more than 25 times the mass of our sun. A black hole is a region of space-time that has a gravitational acceleration so large that light can't even escape, and it's created from the remains of a massive supernova explosion. Now you can see here, this is the first picture we've ever been able to take of an actual black hole. It's Messier 87, and it was taken on April 11, 2018. It's the first direct visual evidence of the supermassive black hole. Now, what a black hole actually looks like, if you were to take a look at the space-time bending of it, is this bottom picture here. So what we see is the warping of space-time due to an immense gravitational force. So everything is going to be sucked into this little gravitational well. Nothing can escape the gravitational pull of a black hole. And that brings us to our final diagram. So everything's the same as when we went previously to that guy. But instead of doing that step, our star is so massive, we're going to go straight to the black hole. We're going to go massive supernova explosion, black hole. Now, we can't actually see a black hole. We can only detect the gravitational effects created by one. Their gravity is so strong, they can swallow up surrounding planets, stars, and light. Now, keep in mind, it's not like a vacuum cleaner going around sucking planets into its black hole. What happens is that the planet would simply get trapped in the gravitational well of the black hole, and it wouldn't be able to escape the gravitational pull. Now, the last thing we're going to do is we're going to talk about HR diagrams. Stars can be arranged on a chart based on their luminosity and temperature using a Hertzsprung-Russell, or HR diagram. And you can see right here, that's an HR diagram. Now, on our HR diagram, we have lots of information, but the main thing that we can see is this main sequence right there. And our star is located right there. Now, a main sequence doesn't mean that the star starts up here and goes down and finishes down there. But what it means is when it's fusing hydrogen to form helium, it's going to be found somewhere on this chart. Now, where on this chart depends on how big it is, how hot it is, etc. You can see we have luminosity on the left-hand side right there, and we have temperature on the bottom right there. So if something is really bright and really hot, it's going to be located right there. That's going to be 60 times the mass of our sun. That's going to be a really bright object and a really hot object. On the other end of the spectrum, we're going to have really cold. Now, cold in this respect is 3,000 degrees Kelvin, and not very bright is going to be located on this end here at the bottom. So this guy right here is going to be our least bright and coolest object. Now, when the star is done fusing together hydrogen to make helium, then it leaves the main sequence and it becomes one of these guys here, our supergiants and our giants, as well as our white dwarfs, which are generally going to be the final product. So if you want to take a look at the sequence of events, it's more like you go from here to here to here. So let's review. About 90% of stars are located on the main sequence. Main sequence stars form helium from hydrogen atoms in their core. Once the star stops fusing helium from hydrogen atoms in their cores, they leave the main sequence. When they leave the main sequence, they will form giants, supergiants, and white dwarfs. How long a star stays on the main sequence depends on their size. Larger stars burn their fuel faster and therefore spend less time on the main sequence compared to lower mass stars. And here's our diagram in its entirety. Depending on how big your star is, you're either going to take this first route and go up top and eventually become a white dwarf, or you're going to take the second route and eventually either become a neutron star or a black hole, depending on how large you are. So what I'd like you to do before you finish the lesson is take a look at this inquiry activity. It's a really interesting look at the HR diagram, and it gets you thinking about what we've talked about so far in this lesson. Once you've done that, your lesson on the life and death of stars will be concluded.